Hello everyone. Today I am going to start second lecture on second modulo, that is Fourier series, third semester engineering mathematics. Course is transform calculus, Fourier series and numerical techniques. Code is 18MAT31. In the last lecture I have started this modulo, and in that we will discuss the introduction of Fourier series, where we study about where we use the Fourier series, when we use the Fourier series, and the definition of periodic functions and trigonometric series and Euler's formulae for the coefficient of Fourier series and some conditions of Dirichlet's conditions, and also I have solved one example to obtain the Fourier series for the given function. Today we will explain some more example to find the Fourier series. Second example is obtain the Fourier series for the function x square in x lies between minus pi to pi, and hence deduce that pi square, first one, pi square by 12 is equal to 1 by 1 square minus 1 by 2 square plus 1 by 3 square minus 1 by 4 square plus and so on. Next is pi square by 6 is equal to 1 by 1 square plus 1 by 2 square plus 1 by 3 square plus 1 divided by 4 square plus and so on. Next one is pi square by 8 is equal to 1 by 1 square plus 1 by 3 square plus 1 by 5 square plus 1 by 7 square plus and so on. Here first we have to obtain the Fourier series for this function, that is x square. After that we have to deduce these expansions. Let us go to the solution. The Fourier series of f of x having a period 2 pi is given by f of x is equal to a0 by 2 plus summation n running from 1 to infinity an cos n theta plus summation n running from 1 to infinity bn sin n theta, and name this is equation as 1. Now where Fourier coefficients, means these coefficients a0, an, bn are given by the Euler's formulae. Those are a0 is equal to 1 for a0 is equal to 1 by pi. Here our in given example x lies between minus pi to pi, therefore our limits is minus pi to pi, integration from minus pi to pi f of x dx. We know that f of x is x square, therefore a0 is equal to 1 by pi integration from minus pi to pi x square dx. Then integration of x square is x cube by 3, therefore a0 is equal to 1 by pi x cube by 3, limits from pi to minus pi. We know that 1 by 3 is constant, take outside the limit, therefore a0 is equal to 1 by 3 pi into, first apply the upper limit, therefore it will be pi cube minus apply the lower limit minus pi cube, minus into minus plus it will be, therefore it is 2 pi cube, therefore a0 is equal to 2 pi cube by 3 pi. Here 1 pi cancel with this denominator pi, we get a0 is equal to 2 pi square divided by 3. In our Fourier series we have a0 by 2, therefore find a0 by 2. Therefore a0 by 2 is equal to, take this 2 in this side, we get a0 by 2 is equal to pi square divided by 3. Now find the an and bn. Now an is equal to 1 by pi integration from pi to minus pi f of x cos nx. Here f of x is x square. Therefore, an is equal to 1 by pi integration from minus pi to pi x square cos nx. To solve this one, we have to use the Bernoulli's rule. We know that what is Bernoulli's rule and how to apply that one. Here x square cos nx. Consider x square as a differentiating part and cos nx as a integrating part. Then n is equal to 1 by pi, keep as it is. Keep differentiating part as it is and integrate cos nx. We know that integration of cos nx is sin nx divided by n. Then minus differentiate this x square. Differentiation of x square is 2x into, again integrate this sin nx by n, not cos nx. 1 by n is constant, keep as it is. Integration of sin nx is minus cos nx. Cos nx divided by n. Already here we have n here. N into n is n square. Therefore, it is 2x into minus cos nx divided by n square. Next, again differentiate this 2x. We get 2 into, then integrate this one minus as it is. Integration of cos nx is sin nx divided by n. We have already n square here. N into n square into n is n cube. Therefore, 2 into minus sin nx divided by n cube. Limits from minus pi to pi. We know that sin pi value is 0. Therefore, the first term and the last term will be 0. Only we have this middle term to apply this limits, so that an is equal to, and before that we have to take n cube common in these three terms. When we take n cube common, it here coefficient of n sin nx will be n square and coefficient of minus cos nx will be n. According to that, n is equal to 1 by pi n square. I am taking n square common from all these three terms and multiplying this middle term to n. We get n into 2 pi cos nx. Limits from minus pi to pi. It will be positive because minus into minus plus. Therefore, only we have 1 by pi n cube into n into 2x into cos nx. Limits from minus pi to pi. Now take this n outside this bracket because n is constant. To apply this, n and 2 is constant for to apply this limits. When we take n outside this, one n cancel with this denominator n cube. Therefore, it will be 2 divided by pi n square. Apply upper limit, it will be pi cos n pi minus again pi cos of minus n pi. We know that cos of minus theta is cos theta. Therefore, cos of minus n pi is equal to cos n pi. Therefore, it is pi cos n pi minus pi cos n pi. Here lower limit is minus 5. Therefore, it is minus into minus plus, because upper limit minus lower limit, again we have my negative sign. Therefore, it is minus into minus plus. It will be pi cos n pi plus pi cos n pi. It will be 2 pi cos n pi. Therefore, an is equal to 2 by pi n square as it is 2 pi cos n pi. Here pi, this pi cancel with this denominator pi. Then 2 to the 4 divided by n square. We know that cos pi value is minus 1. Here we have cos n pi. Therefore, it is 4 into minus 1 raised to n divided by n square. This is the value of an. Next, we have to find the value of bn. For that, next bn is equal to 1 by pi integration from minus pi to pi f of x sin nx dx. Bn is equal to 1 by pi integration from minus pi to pi f of x is x square sin nx dx. Again we have to apply the Bernoulli's rule to find this integration. Again consider x square as differentiating part and sin nx as integrating part. Then bn is equal to 1 by pi, keep differentiating part as it is x square, integrate this sin nx. We know that so integration of sin nx is minus sin nx divided by n minus differentiate this 2x, we get to 2x into again integrate this cos nx. integration of cos nx is sin nx by n. Again already we have n here, therefore it is minus sin nx divided by n square, plus differentiate this 2x, we get 2, and integrate this one, minus cos nx divided by n square into n is n cube. Therefore it is 2 into minus cos nx divided by n cube, limits from minus pi to pi. Now we know that sin n pi value is 0, therefore this middle term, whole term will be 0, so that we have to apply only first term and last, we have to apply limits for first and last terms. Keep 1 by pi as it is. From this one, from first term, keep take 1 by minus 1 by n outside the limit, because it is a constant. X square into cos nx, we have to apply the limits. It will be pi square cos n pi minus, our lower limit is minus minus pi whole square is plus pi square, therefore it is pi square cos n pi. Again cos of minus theta is cos theta, therefore it is pi square cos n pi minus cos square pi square cos n pi, plus middle term is 0, plus take n cube outside, it will be 2 by n cube. Cos n pi value is cos of minus theta is cos theta, therefore before applying limits, take this negative sign outside, it will be minus 2 by n cube. This is minus, not plus, minus 2 by n cube. Apply upper limit cos n pi minus lower limit cos of minus theta is cos theta, therefore it is cos n pi minus cos n pi. Here pi square cos n pi minus pi square cos n pi is 0. Again here cos n pi minus cos n pi is 0, therefore whole term is 0, therefore bn is equal to 0. Thus by substituting these values of a0, an, bn in 1, the Fourier series is given by f of x is equal to, here f of x is x square, which is equal to pi square by 3 plus summation n running from 1 to infinity 4 into minus 1 raised to n divided by n square into cos nx. This is the Fourier series of a given function, that is x square. Next we have to deduce the given expansion. For that, consider this is equation 2. Next put x is equal to 0 in equation 2, means this, in this equation put x is equal to 0. See what we get. F of 0 is equal to x is 0, x 0 square is 0 is equal to pi square by 3 plus summation n running from 1 to infinity 4 into minus 1 raised to n divided by n square cos n 0, because x value is 0 here. X square is again 0, 0 square is again 0, which is equal to pi by 3 plus summation n running from 1 to infinity 4 into minus 1 raised to n divided by n square as it is. Cos 0 value is 1, therefore it is simply pi square by 3 plus summation n running from 1 to infinity 4 into minus 1 raised to n divided by n square. Now take this pi square by 3 in this side, we get minus pi square by 3 is equal to, here 4 is constant. To apply this summation, take this 4 outside the summation, this is 4 into apply minus 1 raised to n by n square. For minus 1 raised to n by n square, this summation we get minus 1 by 1 square, because substitute first n value as 1, we get minus 1 by n square. Next apply n as 2, we get 1 divided by 2 square, then apply n as 3, it will be minus 1 by 3 cube plus minus 1 by 4 cube minus and so on. Therefore take this 4 in this side and apply this negative sign here, or taking negative sign on both the sides, we get pi square by 12 is equal to 1 by 1 square minus 1 by 2 square plus 1 by 3 square minus 1 by 4 square plus and so on. See, this is the first result. Next one. Now put x is equal to pi, in equation 2 we get f of pi is equal to, x value is pi square is equal to pi square by 3 plus summation n running from 1 to infinity 4 into minus 1 raised to n divided by n square into cos n pi. Now pi square is equal to pi cube by 3 plus summation n running from 1 to infinity 4 into minus 1 raised to n divided by n square. Since cos n pi value is minus 1 raised to n, therefore minus 1 raised to n here it is, and minus 1 raised to n into minus 1 raised to n, it will be minus 1 raised to 2n, which is equal to 1. Therefore, and this 4 is constant, take outside this summation and take this pi square by 3 on this side. Pi square minus pi square by 3 is equal to 4 into summation and running from 1 to infinity. This 2 value is 1, therefore 1 by n square. Now it will be, after solving this one, we get 2 pi square by 3, which is equal to 4 into summation n running from 1 to infinity 1 by n square. Now apply first n as 1, next n as 2, n as 3, like that we get pi square by 6 is equal to summation 1 by n square plus summation 1 by 2 square plus summation 1 by 3 square plus summation n divided by, pi square by 6 is equal to 1 by 1 square plus 1 by 2 square plus 1 by 3 square plus 1 by 4 square plus and so on. This is the second expansion. Next one is, now to find the last result, we have to add the equation, means this equation, first reduction, and this second one. We get pi square by 12 plus pi square by 6 is equal to 2 into 1 by 1 square plus 2 into 1 by 3 square plus 3 into 1 by 5 square plus and so on. Because see here, in first term we have 1 by 2 square and minus 1 by 2 square, 1 by 4 square values are negative, and in this second reduction 1 by 2 square, 1 by 4 square values are positive. When we add these two terms, they cancel each other. Next, here 1 by 1 square, 1 by 3 square and so on values are there. Here also 1 by 1 square, 1 by 3 square values are positive. Therefore, it is 2 into 1 by 1 square plus 2 into 1 by 3 square plus 2 into 1 by 4 square plus and so on. Next, take 2 common in these all terms. We get 1 by 1 square plus 1 by 3 square plus 1 by 5 square. Next term is 1 by 7 square plus and so on. Then take this 2 on this side. We get pi square by 8 is equal to 1 by 1 square plus 1 by 3 square plus 1 by 5 square plus 1 by 7 square plus and so on. Next, example 3. Obtain Fourier series expansion, Fourier expansion of f of x, which is equal to e raised to minus ax in the interval minus pi to pi, and hence deduce that cosec h pi is equal to 2 by pi into summation, here n running from 2 to infinity, minus 1 raised to n divided by 10 square plus 1. Solution. We know that the Fourier series expansion is f of x is equal to a naught by 2 plus summation n running from 1 to infinity a n cos nx plus summation n running from 1 to infinity bn sin nx, and a naught is equal to 1 by pi. Here limits are minus pi to pi, therefore integration from minus pi to pi f of x dx is equal to 1 by pi integration from minus pi to pi. Here f of x value is e raised to minus ax into dx. Now we have to integrate this e raised to minus ax. It will be 1 by pi into e raised to minus as divided by minus a, limits from minus pi to pi. Here minus a is constant. Take outside this limits. Then after applying the limits, which is equal, this is equal to e raised to a pi minus e raised to minus a pi divided by a pi, which is equal to, here multiply and divide this term to 2, we get 2 sin h a pi divided by a pi, because we know that e raised to x minus e raised to minus x divided by 2 is sin hx. To write this, to use this result, just you have to multiply and divide this term to 2, then you get 2 into sin h a pi divided by a pi, which is the value of a naught. Next, an is equal to 1 by pi integration from minus pi to pi f of x cos nx dx, which is equal to 1 by pi integration from minus pi to pi e raised to minus ax cos nx dx. Again we have to use the one result to solve this integration. As I already given this important result, we have to use these results here. See here, integration of e raised to ax sin bx dx is e raised to ax divided by x square plus a square plus b square into a sin bx minus b cos bx, and integration of e raised to x into cos bx dx is equal to e raised to ax divided by x square plus a square plus b square into a cos bx plus b sin bx. And we know that sin pi value is 0, means sin n pi is also 0. Sin pi value is minus 1, therefore sin n pi value is minus 1 raised to n. We know these two results. You have to remember these two results when you have the terms in integration as e raised to ax and sin bx or cos bx form. Then an is equal to that is an is equal to 1 by pi e raised to minus ax divided by x square plus n square, a minus a into cos nx plus n into cos sin nx. Here a value is a and b value is n here, and limits from minus pi to pi. Apply the limits, we get 1 by pi into e raised to minus ax divided by n square, a square plus n square into minus a cos n pi plus n sin n pi, then minus e raised to x divided by a square plus n square minus a cos n pi minus n into sin n pi. First we have to apply the upper limit to this term, next minus lower limit to this term. Next, after simplification of this one, we get 1 which is equal to 1 by pi into e raised to minus a pi divided by a square plus n square minus e raised to a pi divided by a square plus n square into a cos n pi, which is equal to a divided by pi into a square plus n square into e raised to minus a pi plus e raised to minus e raised to a pi into minus 1 raised to n, because cos n pi value is e raised to minus n, and take a square plus n square common in these two terms. We get a by pi into, here already pi is there, and take this a here, a by pi into a square plus n square into e raised to minus pi minus e raised to minus a pi into minus 1 raised to n. We know that e raised to a pi minus e raised to minus a pi divided by 2 is cos sin h a pi. Therefore, to take this result, just multiply and divide this term to 2. We get 2a by pi minus 1 raised to n sin h a pi divided by a square plus n square, which is the value of an. Next we have to find the bn. Bn is equal to 1 by pi integration from minus pi to pi f of x sin nx dx, which is equal to integration from minus pi to pi e raised to minus ax sin nx dx. Next is bn is equal to 1 by pi. Again apply that result, e raised to minus a pi. Here you have to use the result, integration of e raised to ax into sin nx dx. And using that we get 1 by pi as it is, and e raised to minus ax divided by a square plus n square into minus a into sin nx minus n cos nx, limits from minus pi to pi. Now we have to apply the limits here. 1 by pi, here we have to write equal to sign, equal to 1 by pi into e raised to minus, first apply the upper limit to this term, after that minus lower limit, e raised to minus a pi divided by a square plus n square into minus a sin n pi minus n cos n pi minus e raised to minus e raised to a pi divided by e raised to a square plus n square into minus a sin n pi minus n cos n pi, which is equal to 1 by pi into, on simplification we get 1 by pi into e raised to a pi divided by a square plus n square minus e raised to minus a pi divided by a square plus n square into n cos n pi. Now take this a square n square common, we get n into n divided by pi a square n square e raised to a pi plus minus e raised to minus a pi into e raised to minus 1 minus 1 raised to n. We know that e raised to a pi minus e raised to minus a pi divided by 2 is sin a pi. To use this result, multiply and divide 2 to this one, we get a bn is equal to 2n by pi minus 1 raised to n sin h a pi divided by a square plus n square, which is equal to 2n by pi minus 1 raised to n divide into sin h a pi divided by a square plus n square. Now this is equation B. Now we have to substitute all this coefficients value, that is a naught, an and bn in equation 1, means Fourier series. We get f of x is equal to 2 sin h a pi divided by pi into 1 by 2a plus summation n running from 1 to infinity minus 1 raised to n a divided by a square plus n square into cos nx plus minus 1 summation n running from 1 to infinity minus 1 raised to n into n divided by a square plus n square into sin n x. This is the Fourier series. Next we have to find the cosec, we have to prove that cosec h pi is equal to this one. For that, for x is equal to 0, a is equal to 1, the series reduces to f of 0 is equal to 1, which is equal to, because e raised to 0 is 1, so that f of 0 is equal to 1 is equal to 2 sin h pi divided by pi into 1 by pi plus summation n running from 1 to infinity minus 1 raised to n divided by 1 plus n square. Put x as 0 and a is 1, we get this step. After that, take sin h pi divided by pi in this side, we get only sin h pi, we get 1 divided by sin h pi is equal to 2 by pi into this remaining term as it is. We know that 1 divided by sin h pi is cosec h pi, which is equal to 1 by pi into 1 by 2 plus summation n running from 1 to infinity minus 1 raised to n divided by 1 plus n square. Then cosec h pi is equal to 2 by pi into 1 by 2 minus 1 by 2. In our proof they are given this our summation running from 2 to infinity, so that to write this summation n running from 1 to infinity to 2 running from n running from 2 to infinity, just we have to take here minus 1 by 2, because when we apply n is equal to 1 to this expansion, we get it as a minus 1 by 2. Therefore 2 by pi into 1 by 2 minus 1 by 2 plus summation 2 running from 1 to n running from 2 to infinity minus 1 raised to n divided by 1 plus n square. 1 by 2 minus 1 by 2 is 0. Therefore, 2 by pi summation to n running from 2 to infinity minus 1 raised to n divided by n square plus 1, which is the required result. This is the proof, that is cosec h pi is equal to 2 by pi summation n running from 2 to infinity minus 1 raised to n divided by n square plus 1.